So today I'm gonna introduce homogeneous equations. Of course, they are differential equations. And they have a common way of representing them. As we know, we're still in first order differential equations. So we will already have like first derivative for the moment. So let me introduce y as a function of x. Okay, so x is going to be the independent variable. And y is going to be the dependent variable. So in my notation, y prime will mean differential of y with respect to x on this introduction. So imagine that we have the following kind of equation. Y prime equals a function of x and y. So this is any kind of first order differential equation in principle. So in order for one of these differential equations to be homogeneous, given a lambda, if we make the following change, if we rescale the variables by lambda, that means that where it was x, we have lambda x, and where it was y, we have lambda y. We have to obtain f the xy again. So that means that the function is homogeneous. Basically, it means that all the factors have the same degree. We will see that with a little example. But for the moment, let me show you that if we have an equation that is homogeneous, that is the f can be rescaled with a lambda and equals the same unscaled function. What does this mean? That means that there exists a change of variable let me introduce it as a v function of x, and here y function of x divided by x. That means that the initial y is going to turn into v times x. So here, notice that initially we have an equation that is written in x and y as a function of x. And now, with the change of variable, we aim at reaching an equation that is going to be written in x and v as a function of x, okay? So let me plug the change into the equation and show you that the change turns the equation, turns an homogeneous equation, homogeneous differential equation, into an equation in separable variables. It's pretty straightforward. So let us start again with our equation. Okay, and let me introduce the change of variable, which is y equals v times x. So in order to obtain what is y tilde or y prime, we only have to differentiate the change of variables. Remember that the prime means differential with respect to x. So this, by using the differential law of product, we have the differential of the first, second without derivation, plus v without derivative, and we have derived the x. So plug this into the equation. And you'll get the v prime times x plus v equals a function of x, and where y was, we will have to put v times x. So now here we're going to apply something. We're going to apply that f is actually an homogeneous function. So notice here that the x in this case is the parameter that was playing the role of lambda. Okay, so bearing that in mind, that means that the f, since it's homogeneous, it's gonna equal an f of, like, if the parameter was going out of the function of 1 and vx. So what does this mean? Well, this actually means that our equation has turned into an equation that for the moment looks simpler. And see this, it's possible to put on the right hand side everything dependent on v. This is only like a function of v. And here we can now safely say that our equation has separable variables. So here, now we turn to the left all the functions in v, and in the right, we can put all the functions in x. So basically, this means that we can integrate this and leave this in terms of this integral, which can be performed in the case that we know an explicit function. So now what I'm going to do is actually applying this change of variable to a specific problem. So yeah, once now that we have proof that any homogeneous equation can be turned into an equation that has separable variables just by using this change of variables, now we can try to put this into an application. So let me solve one specific problem. So the problem is the following. It says we have to obtain a curve that passes through the following point, which is 3, 9, and satisfies the following. One is that the distance from the origin of coordinates to the tangent the tangent to the curve at a specific point equals the absolute value of the coordinate x of that point, that specific point. Okay, so this basically means something like the following. So imagine that we have a curve, let's say something like this, and it passes through the point 3,9. Well, let me paint this a little better so we can put the point exactly. So here and here, okay. Well, for the moment, I just paint the first quadrant. So let's make divisions. Like this is going to be 3, this is 6, and this is 9. 3, 6, and 9. Okay, and it says that it passes through the point 3,9. So something like this and this point. So it's going to be a curve. I have no idea of what kind of curve this is. So let's put a curve like anything like this, for example. I still don't know what kind of curve. This is going to be a curve y depending on x. And it tells me that I choose like a random point. This is the point that passes through. But it says that for any point, let's say xp, yp, if I put the tangent to that point, tangent line to that point, it's a little bit bad. It should pass by the point. Let me see if I can paint it a little better. Okay, so it says that I have to trace the tangent line in that point. So basically what it says that the distance from the origin to that tangent line, let me put this in yellow, and this would be our distance from the origin 0, 0 to this line. Okay, and this is 90 degrees angle, has to be this distance, has to be equal to the distance or the absolute value of the x. So you may start wondering what this curve is. I won't display it until we solve the equation, but this is what the problem is asking from us. So let's try to solve this. So how do we start? Okay, well, it says the distance from the origin of coordinates to the tangent line to the curve and at a specific point equals the absolute value of the coordinate x of that specific point. So basically, we have to translate this into our differential equation world. How do you do this? Well, we have to remind how we calculate the distance from a point to a line. So let me choose the line ax plus by plus c, okay, generic, and a point P that's going to be given by coordinates xp, yp. So the distance from a point to R is defined as the modulo but absolute value, okay, of the value of the valuation of the point in R divided by the square root of A squared B squared. Okay, that's simple mathematics from high school. Okay, so now we say that we are studying the origin. So then the distance from the origin to any line R will be very simple, right? Because in this case, origin will be xp, yp equals 0, 0. So in this case, we'll have the absolute value of C divided by the square root of A squared and B squared has to be equal to the absolute value of X of that of an X specific point. Okay, which is a specific point where the tangent passes by, tangent line. So what do we need now? Well, we need to characterize the coefficients A, B, and C. We need to characterize the coefficients A, B, and C. So how do we do that? Well, we just have to write the tangent line to a curve. So what's the general equation of the tangent line to a curve? Well, the general equation will be the following. It will be y minus whatever the point is that passes through. Let's call it eta psi. We'll have I have to stop the recording now. Okay, so the equation from the tangent line is this one. Here, this is the point, okay, through which the tangent line passes, okay? So the tangent line, what it has is like the slope, which we normally call m, is going to be equal to the differential of y, where y is the equation of the curve to which it is tangent. So that's the main thing we have to know about this tangent line so we can calculate it. So basically, as you can see in the distance, we have in normal form the equation of a line, right? So what we have to do is just to write the equation of our tangent line as the normal form, put it in the normal form. So how do we do this? Well, it's very easy. So we said that on one side, we have that our tangent line is going to pass by this point. So that's going to be the point. I think that's the point, like random point that before I call xp, yp, you can just call it psi eta right now. So, sorry, here is psi and eta. If you want to put it like in order, okay. So this is psi and eta. So what do we have to do? Well, we just have to merely just compare the equations and learn what is A, B, and C. So here we have on one side the tangent line equation. And on the other side, we have the normal form. So just by direct comparison, one can very easily see, if you notice what is accompanying the psi and what is accompanying the eta, that from here, A is gonna be y prime, B it's gonna be -1, and C is gonna be the rest, which is y minus x y prime. Okay, so now we know what we have to put in our distance. So we said that the distance from the origin to our tangent line is going to be z modulo. So it's going to be modulo of c divided by a, which is y prime square plus b square. And this has to be equal to the absolute value of the point x. Okay, so we just have to solve this equation, and very simply we can just take we can square the equation on both sides, so we can get rid of the absolute values. So that means that our equation is merely square equals x y prime square plus 1. So now let me play here a little bit with the equation so we can get like an easier form. So here you will have y squared plus x squared tilde square minus 2yx y prime equals x y prime square plus x. So notice that these two factors are the same here, that we can write, sorry, I'm missing here square and square. So we can write here y squared minus x squared equals 2 times y prime x. And here, notice that we can write the final equation as this equation. And notice that this equation is homogeneous. How do you see this? Well, it's very simple. One can just take a look at the order. So here, order 2, or degree, and here we have degree 2 because we have an x multiplied by the y at each added degree. If you don't see it straightforwardly, you can just do a little check very easily. So in this case, our function xy will be y squared minus x squared 2 times xy. And if we rescale it with the factor lambda, as we said, we will get like lambda square y squared minus lambda square x squared divided by 2 times lambda x lambda y, and realize that we have 2 lambdas here. That's going with this away, and it's becoming exactly the same as we had before. So that means that the equation is homogeneous. So since it's homogeneous, we can actually integrate it by the change of variable that we have introduced before. So, well, let's do it to find out what's the curve that actually we are looking for. So again, we take our equation and what we have to do is to introduce the change of variable that we have mentioned before. So this is the change of variable. So we have to derive it in order to use it. With the derivation rule of the product, we just get this. So introducing the change now. What do? We have like on this side, the v, and on this side, we have the y, but y is now v squared x squared minus x squared divided by 2 times vx xx. Now realize here that you have a common factor here of an x squared. So you do and down. So the x go away. And what does this mean? So this means that we have, as we were saying before, when we introduce these equations, that on this side, we will have purely a function of v. So now let me take the v on the left-hand side to the right-hand side. Minus v, and rewrite the equation as minus 2v squared. So here we have that our equation is becoming simpler and simpler. We have minus 1 minus v squared divided by 2v. Again, this is a function of v purely. And what do we have? Well, we have separate variables. This is a very easy equation now. Sorry, this is x. This is a very simple equation now that we can solve straightforwardly. So we can put the minus sign here. And this equals differential of x divided by x. So we only have to solve this equation, which is quite simple. Sorry, I forgot to put the 2v. So it's 2v differential of v divided by minus. Let's put the minus in there. Differential x divided by x. We only have to integrate this equation, which is very simple and very straightforward. So as you can see, on the left-hand side, we can put some limits if you want. And we can put v0 on v. So we have the logarithm is gonna equal this integral. But realize that in the numerator, you have exactly the derivative of the denominator, except for the sign. So you can just take out the sign and you just have the logarithm of 1 v squared between these two limits. Okay, so we have the logarithm of x minus logarithm of x0. It's minus logarithm of 1 plus v squared plus logarithm of 1 plus v0 squared. Okay, so realize that here we can put all the dependence on variables, and here we can put all the constants. Realize that these are all constants of integration. And I can actually put them all together. So let's do it. And let's call it all logarithm of k as any constant of integration. So now we have the logarithm of 1 times v squared multiplied by x equals logarithm of k. And from here, we obtain that 1 plus v squared is exactly k divided by x. And if we make the change of variables, what do we get? We get that 1 plus v. Remember that v was y divided by x equals k divided by x. So y divided by x squared will be k minus x divided by x. And y will be k minus x multiplied by x. So that means that we have a result of this kind. What is this? Well, this is a circumference. It's a circumference, and the k, which is a constant of integration, can be used, can be fixed by the fact that the curve passes through the point 39. So, well, if we just put that into our equation, we will just obtain k 3 times k equals 0, and that k is exactly 30. So this means that our equation that we're looking for is this one, which can be rewritten in the following way. So basically, it's a circumference that has the center in 15, 0, and the radius 15. So it's easy to spot the curve and to check out that actually one can see. Let's see that this is 5, 10, 15, 5, 10, 15, and we have the center here. Okay, and the radius is gonna be something like this. If only I could paint it a little better, you could see it. But well, imagine so. So imagine that we have a random point, and we're gonna trace tangent line right there. This point has an absolute value of x that is exactly the distance from the origin to this tangent.